Welcome back. While the naive set theory leads to paradoxes or inconsistencies, shown by the English philosopher Bertrand Russell, we will use this version of set theory. Sets can be represented graphically using Venn diagrams named after the English mathematician John Venn. In a Venn diagram, the universal set denoted by U is represented by a rectangle. Inside the rectangle, circles or other geometrical figures are used to represent sets. Sometimes points are used to represent particular elements of the sets. For example, here is the set of vowels. So that's the universal set. That is the set of vowels V. And here are the elements of the sets of the set V. The set A is a subset of a set B if and only if every element of A is also an element of B. We use the notation A cup underline. So this represents subset. A subset of B to indicate that A is a subset of B. Note that A subset of B if and only if the following quantification is true. For all x such that x is an element of A, then x is an element of B. So for every x, if x is an element of A, then x is an element of B. That is what makes A subset of B. In other words, to show that A not a subset of B, all we need is one element from A which is not in B. In a summary, showing that A is a subset of B, what do? To show that A is a subset of B, show that if x belongs to A, then x also belongs to B. Showing that A is not a subset of B, how do we show? To show that A is not a subset of B, all you need is a single element of A which is not an element of B. Here is a Venn diagram representing subset. So the rectangle is your universal set, B is your bigger set, A is subset of B. So it's drawn inside the circle for B. That's the circle for B. A is drawn inside B. Prove that for every set S, empty set is a subset of S, and B, S is a subset of S. These are two notions we want to prove. So remember, to prove that A is a subset of B, what you need to show is that for every x, if x is in A, then x is in B, you see. So first let's see. We want to prove that the set, empty set, is a subset of B, of any set B. This is what we want to show. That is, we want to show that for every x such that x is in phi implies x is in B. Note, empty set has nothing in it. So this condition is vacuously true. So this quantification is vacuously true. Therefore, empty set is a subset of B. Okay, this happens for any set B. We have empty set is subset of B. All right. The other situation is to show that S itself is a subset of S. For any set S, we want to prove that S is a subset of of S. Well, we want to show this quantification, you see. So we want to show that for every x in S, x is in S. Well, that's a tautology. Every element of S is in S. Okay, tautology means true for every x. So, or you can say, I don't want to use the word tautology. This is true. That's a correct way of putting it. For every x, if x is an S, then x is an S. Therefore, S is subset equal S. All right. We say that A is a proper subset of set B if A is a subset of B but A is not equal B. So, denote A is a proper subset of B by writing just the cup without the line underneath. Note that for A in B's proper subset of B to be true, every element of A must also be an element of B, and there must exist an element in B which is not an element of A. In other words, A is a proper subset of B if and only if, for every x, if x is an element of A, then x is an element of B. So that makes A a subset of B. In addition, and there exists an element x such that x is in B, but and x is not an element of A. You see what this feature says. Let's see it using Venn diagram. What that means is you need, let's draw a Venn diagram. So suppose I have my universal set, right? So this is my universal set U. All right. Suppose I have a set B. Okay. Now you see, we already know so far that every set is a subset of itself. So so B is a subset of B, but I want some set which sits inside B, but it is not whole of B. So suppose my set A contains two elements, and the set B contains three elements, 1, 2, and an element outside. So now capital A is a proper subset of B. So here is a Venn diagram that we like, showing two sets to be equal. To show that two sets are equal, well, when are two sets equal? When the every element here is here, as well as every element is here from B is here. That is, A is a subset of B and B is a subset of A. Okay, so that's how you show two sets are equal. You show that each set is a subset of the other. The size of a set. Let S be a set. If there are exactly n distinct elements in S, where n is non-negative integer, we say that S is a finite set and that n is the cardinality of S. Cardinality is the number of distinct elements. The cardinality of S is denoted by bars. Okay, bar S, vertical line. If S is not a finite set, then S is said to be an infinite set. So that is, there is no finite number that you can say is the cardinality. Say you give me a number 100, well, I can give you a set with 101 elements and so on. So a set is said to be infinite if it is not a finite set. Write down 4 examples of finite sets and write down their cardinality. So they want four examples of finite sets. So let's see. Let me say set A consists of 1, 2, 3, 4. This is one set. Let's set B consists of -1, -2, -3, -4, -5. So the cardinality of A is 4. Cardinality of B is 5. B has 5 elements, you see. There are many. Well, so let's say, let O be the set of odd integers, odd positive integers less than, say, 10. So notice how many positive odd numbers do you have? 5. Cardinality of O is 5. Suppose I take the set of all positive integers until 100, starting from 1, right? Positive integers. So cardinality of C is 100. So do I have 4 finite sets? Yes. Power sets. Have we seen, by the way, any infinite sets? Of course we have seen. The set of natural numbers, right? This goes on forever. This set cannot be bounded at any position. It keeps going. This is a set of natural numbers. And then what about the set of integers, right? Which is unbounded in both directions. So here are examples of infinite sets. And here are examples of finite sets. Power set. Given a set S, the power set of S is the set of all subsets of the set S. Power set of S is denoted by P of S. Okay, let's come to this exercise and we'll answer this question in just a minute. Let's continue in our next video.